afternoon again, everybody. I'm Dr. Kerry Hall, and today I have the pleasure of introducing my advisees, Adam Riddell, Donald Shaw, Jacob Rankin, and Josh Belbach. They found this project on their own, so I'm going to let them introduce it.
Thank you, Dr. Hall. Our senior project, we designed the Camp Atterbury Barracks. My name is Josh Belbach.
Donald Shaw.
Jacob Rankin.
And I'm Adam Riddell.
Camp Atterbury was founded in 1942. It's currently a training ground for the Indiana National Guard. A barrack is basically a sleeping quarters or residence hall for military personnel, and it's needed because the current ones are outdated, and also there's a need for expansion.
So before we could start on the design of our structure, we provided some pre-design information. This included architectural plans, soil boring, and topographical information, as well as the Department of Defense design criteria. The scope of our project was broken up into 3 different categories: the site work, structural, and cost estimation. Grading and hydrology were completed for our site work. Geotechnical, roof system, masonry wall, interior column, and slab design were all designed for our structure. And then at the end of our project, we did a total cost analysis for our project. So the proposed location for our structure is about 45 minutes south of Indianapolis in Edinburgh, Indiana. On the right-hand side, you can see an aerial view of our land. This land is fully undeveloped.
This is a topographic map of the existing surface, where the green lines represent 5 feet elevation changes and the purple lines represent 1 foot elevation changes. The site originally used to drain from the north to south, so that would be the top of this picture to the bottom of the picture. This is a topographic map of the proposed surface. It was designed so that the site would drain into the north channel seen at the top, or the south channel seen at the bottom, and then collect into the west detention basin. This is an existing roadway, and this is the parking lot, and this is the Camp Atterbury Barracks. The parking lot and the barracks look like they're outlined because in a topographic map, that just means that they're the same elevation. The existing and the proposed topographic maps were overlaid, and the grid method was used with a 50-foot square grid, where each square is 50 feet. And it was determined that 30,000 cubic yards of soil will be left over after the site has been graded to finished. And that will be used for future construction and stored on site until then.
So for the hydrology portion of the project, we started off with the Indianapolis Stormwater Design and Construction Specifications Manual, and we use that in conjunction with the Department of Defense's design criteria. Based on those 2 criteria, we came up with our design storm frequencies. Our design storms for the culverts, enclosed storm drains, and open channels were all 10 years, and our detention basin required 4 different design storm frequencies of 2, 10, 25, and 100 years. So the first thing we looked at was the roof drainage. The first pipes that we sized were the riser pipes, which are the vertical pipes that run from the top of the roof all the way down, and they connect to the pipes that run underground, parallel and perpendicular to the building. These pipes were sized for a 10-year rainfall event. All these pipes were sized the same for redundancy purposes, and they were all sized using the maximum flow rate possible on the roof. The riser pipe size was chosen to be 4 inches. This is a typical location plan for all of our riser pipes. We actually needed 60 of them based on the different architectural features of the roof. As you can see in the schematic, there's different hips, valleys, and ridges, and based on those are where they're draining into the riser pipes. This is a snapshot of our Autodesk Storm and Sanitary Sewer Analysis Model, also known as SSA. As you can see here, the green hatched-in areas are our watershed areas. The black dashed lines connect the watershed areas to where they're draining to. The black solid lines are culverts, channels, and pipes. And the red dots are junctions that connect all of these different parts. So another thing we looked at was the underground pipes for the roof drainage. We actually used this because we wanted our water to not go across the grass for icing purposes. As you can see in this colored schematic, the red pipes are going to be 8 inches in diameter, the blue pipes will be 10 inches in diameter, and the green pipes located on the north and south side will be 12 inches in diameter. these pipes were also sized for a 10-year rainfall event, but the maximum flow rate in these pipes was dependent on the number of risers that emptied into each one of them. That's why you see on the north and south side that those pipes are bigger. Those pipes on the north and south side were joined down to cut down on construction and material costs. Our site also required that we had channels on either side, the north and south side of the building as shown in the grading plan. We chose to have our channels be exactly the same for construction purposes and also because the watershed areas that we're emptying into them were nearly identical. We chose our channel to be trapezoidal in shape, earth lined with a bottom width of 2 feet, a flow depth of 2 feet, and a slope of 1.5 horizontal to 1 vertical. Our site also required that we have 3 different culverts, one on the north side that runs under the parking lot and the existing roadway that will be 22 inches in diameter, one on the south side that runs under just the parking lot that will be 24 inches in diameter, and another on the south side that runs under just the existing roadway that will be 26 inches in diameter. All of these culverts will be constructed of reinforced concrete. They will all have smooth, tapered inlet throats. Rip wrap will be placed around the inlets and outlets of these culverts to control on potential erosion issues. And backfill around all of these culverts will be with granular material and will be vibrated in for proper compaction, and that will also cut down on our potential erosion problems. Our site also required that we have a detention pond. This detention pond would make sure that we were able to control the flow as it's going into that creek. As you can see in this top view, our length is 118 feet and our width is 168 feet with a top of bank elevation of 712 feet and a bottom elevation of 709 feet, which gives a maximum depth in the detention pond of 3 feet. We designed our detention pond to be trapezoidal in shape, and it'll be placed on the west side of the site nearest to the creek. It will allow 3 inches of water to stand in it at all times for water quality purposes. The detention pond itself is actually going to be 3 foot. It will have a 3 foot maximum depth, but that 3 inches of water will stand in it at all times to ensure that we're releasing quality water into that creek. An outlet structure was also necessary to control the flow into that creek because we have to have a lower flow rate going into the creek post-construction as opposed to pre-construction. Our outlet structure has a 12-inch diameter orifice with a 4-foot total crest length weir at the top. It'll be placed 3 inches from the bottom of the detention basin, as said before, and an 8-inch diameter pipe will be required to carry the flow from the orifice to the outfall at the creek.
So this is the roofing system. It's a plan view. These vertical lines right here and these numbers are all different types of trusses. The roof has a lot of hips and valleys and different pitches and different ridge elevations, so it's very complex. So we need a total of 9 different types of trusses. And right here, it's mirrored across this line. So these over here are also truss type 1, just like these. So once we got all the geometry, all the loading that we needed for our truss, for our roof system, we modeled it in a structural software like this. And then we put this is one section. And all 3 sections come together like this. But since it's an H-shaped building and all 3 sections are very similar, they're nearly identical actually, so to simplify the process, we only analyzed one portion of the building. So after we put out everything in the program, we ran it. We had to do several iterations to find correct sizing, but this is what we come up with. These lines right here, these colors correspond to this legend over here, and the top is basically, it's very near capacity, but everything is under capacity. And these over here are less stressed, so they're very low on the low end of capacity. So during our design, we did have members failing. So in order to fix that, we had to look at each truss individually to see where it was failing and why. So this right here is truss 1 from the roof plan, and we can actually go in there and see for different loading scenarios why it's failing and how it's failing, different things like that, and we can adjust accordingly. And down here, it's also truss 1, and we can also look at the deflections of the truss. So even if it meets strength requirements, we still need to look at the deflection of the truss to see if it meets code. Masonry wall runs the whole exterior of the building and some portions of the interior. Its primary purpose is to hold the trusses and the roof system and also act as the lateral supports for the building so it would resist the seismic and wind. It is broken up into 16-foot sections per code. This is due to here is actually our worst case scenario. These openings right here are two doorways right on top of each other, so that made it very big openings in the masonry block. That's what controlled. We had a 10-inch masonry block with grouting and reinforcement every 3 feet. This is a pilaster. Pilaster is a column integrated into the wall, and this is done so that it will support, the exterior of the building will support the second floor gravity loads. So this is a graphic from the International Masonry Institute. So these blocks right here are integrated into the wall, and they're going to be filled with grout and rebar for reinforcement.
So roof loads were designed to be carried from the roof decking to the purlins, and then to the trusses, and then the masonry walls, and finally to the continuous wall footings. The masonry walls also were designed to carry the lateral forcing. Therefore, the interior structure carried the floor loads from the slab to the joist to the girders, and then to the columns, and finally to the column foundation. This is a plan view of the Camp Atterbury Barracks, and the circles represent the locations of the columns. It's important to note that this 1/3 is equal to the other 2/3 of the building. Therefore, we only analyze this 1/3 because the design will be identical for each of the other 2/3. This is the location of the girders, and this will be the location of the joist. And this will be the second floor slab. Volcraft design manual was used to design the floor system. A deck type of 1.5 VL22 is chosen. That just means that it's a screw-in type deck. A thickness of 2 inches and a slab depth of 3.5 inches and reinforced concrete strength of 3 KSI with a normal weight of 145 PCF was chosen for our design. It was also designed to be reinforced with welded wire fabric. This is a plan view of the location of the steel joist, where the colors correspond to the colors in the schematic. They were designed to span a range of 7 feet to 30 feet. The AISC steel manual was used to design these, and channels were chosen as the member site. This is the location of the steel girders, where again the colors correspond to the location in the schematic. W sections were designed using the AISC steel manual, and they were designed to span a range of 57 feet to 18 feet. The steel columns were designed to be hollow rectangular steel sections. That's what the HSS stands for. And this is a plan view of their location, where again the color corresponds to the location of the schematic. And it's also important to note that these purple circles are the location of the masonry pilasters. These are not the HSS steel columns.
So the first step in the geotechnical process is site exploration. We're provided a set of boring logs which contain this information. From there, we were able to determine an N value and a soil classification for our soil. The N value corresponds to the blow counts taken during the drilling process in the field, which our value came out to be 10, and the soil classification for our soil was lean clay. From those two values, we were able to calculate a bearing capacity for our square footings and our wall footings. Our bearing capacity for our square footings was 3,100 PSF, and for our wall footings, it was 2,600 PSF. These all had a factor of safety of 3. So shown here is a cross-section view of our 11 by 11 foot square footing. So given a load of 370 kips that was produced and transferred from the column to our foundation, we were able to calculate the square area of the base of our footing given the bearing capacity of 3,100 PSF. Once we had our base area, we were able to calculate, starting from top to bottom, our base plate and anchor bolts, which would attach our column to our pier. Once we had our base plate and anchor bolts, we calculated our pier size and the rebar needed to support this pier. So once we had our pier size, we were able to calculate the thickness of this foundation and the rebar needed so that the pier wouldn't punch through our foundation. This process was completed for 3 additional square footings, a 5 by 5, a 6 by 6, and a 7 by 7 foot square footing. The thicknesses of these range from 18 inches to 24 inches, and their loads range from 77 kips to 139.4 kips. This is a cross-section view of our continuous wall footing, which spanned the full length of our masonry wall. The 10-inch thick masonry wall produced a load of 6.4 Foundation needed to be 4 feet wide with a thickness of 12 inches. Number 4 rebar, spaced 12 inch on center, top and bottom, would be used for this foundation. So at the end of our project, we did a total cost analysis for our project. This was broken down into many different categories and subcategories. At the end, we tacked on a 91% location factor. This was due to the Indianapolis region. This gave us a total amount of just under $5.5 million. So the pre-design information was provided, the site work was completed, as well as the structural design and the cost estimate. A grading plan was designed, the hydrology was completed, the roof system, masonry wall, slabs, interior columns, and foundations were all designed with a total cost estimate completed at the end. This is a list of our relevant specifications that we used throughout the course of this project. And we'd like to end by thanking Dr. Kerry Hall, Dr. Jason Hill, Dr. Zane Mitchell, Sean Kofer, Rodney Lax, Donna Moore, and of course all of our family and friends that helped us out through the semester and our whole time during college. And now we'd like to open up the floor for questions.
All right, questions? You're probably gonna have to speak up. It sounds like our batteries are dying on those microphones.
We got a
Are those more batteries? All right, excellent.
I don't know, maybe you said it at the beginning, but how many troops are in there? Is it just berthing, or is there like a galley area?
No, there's mainly 2 sleeping wings, and in the center of the building is kind of like restrooms and storage and other small rooms. But the 2 sleeping wings, we're not sure on specific numbers though. We're just given the general floor plan.
Test.
All right. Put that microphone there.
The site looked like it was out in the middle of nowhere. I didn't see any other buildings or facilities. How far is it from the existing Camp Atterbury? And I assume there's an existing one. And why so far away, I guess?
It's actually not that far away. We were just zoomed in to give you a better idea of what the vegetation looked like in the area, so we could follow that slide up with a grade plan and proposed topo map. So to answer your question, it's actually just right across the road. That's where the rest of the Camp Atterbury barracks are.
They actually already have some roads there. Other questions?
Yeah, what specific changes did you have to make to your hydrology to meet the stormwater criteria? Like, was it difficult, or did you meet them right off the bat?
We had to make changes once we moved it to the SSN model, mainly in the culverts. The pipes and everything was based on the rational method, but our assumptions that were made when we did our hand counts for the culverts were wrong, so we changed our culverts when we plugged it into the SSN model.
For the hydro, why did you design to a 10-year event and not something like a 50 or 100-year event?
That's what's given by the Indianapolis Stormwater Manual and also the Department of Defense Manual.
All right, any other questions? Let's give them a hand.